welcome. We have 5 presentations until 1 p.m. Some of them will be in virtual mode and some in video presentation mode. We have also one presentation face-to-face. So we will start with paper 255. The title is The Energy Environmental Efficiency of the Existing Building Stock Through Morphological Constructive Solutions, a case study of a single-family building in Sicily. The authors are F. Bundo, F. Foti, F. Leone, F. Nocera, and L. Savoca from the Department of Civil Engineering and Architecture, Deca University of Catania. This presentation will be in video presentation form. The book existed. The authors are F. Bundo, F. Foti, F. Leone, F. Nocera, and L.
Basewood. The volumetric composition of the building consists of an assemblage of volumes which are developed on several levels, giving a heterogeneous and irregular form to the exterior. It is important to highlight that all the enveloped structure have no thermal insulation, which results in high thermal transmittance value and low inertial capacity. As already mentioned, simulations were carried out using simulation software tools to define the project. Some path and Insight Solar for Autodesk credit were used for the software analysis. For the natural lighting analysis, Lego for Terrace was used. For natural ventilation analysis, Autodesk C8D computational fluid dynamics. And to analyze comfort and heat balance, the design builder based on energy class calculation engine was used. And here you can see the results of some simulation at the actual state, like solar analysis, natural lighting analysis, natural ventilation analysis, and comfort and heat balance. Based on the data obtained from the simulation results, the project was defined. The design solutions is the total air configuration of the building through the application of strategies typical of bioclimatic with building and ecological architecture. Now, the new usable surface area is of 261 meters square. The design strategies have led to redefine the external volumes. The logic of the halls and the internal spatial articulation generated a new architectural form. On the outside, the subtraction of all the elements characterizing the irregularity of the current configurations produced a building with a simple, linear and compact volume. The objective was to obtain an enveloped component with high resistance and thermal inertia. In this way, the well-being of the occupants is guaranteed through the use of Weber of eco-friendly materials with low impact in accordance with basic building ecological. The main effects are converted with a new pack made of heat-insulating blocks in biocomposite of ample line with natural lime pitches. The thermal insulation of the floor against the ground and the roof with heat-insulating strips against the biocomposite of ample line. The replacement of the transparent closure with new windows and doors characterized by a wooden frame with thermal bracket double glazing. In addition, all the openings are fitted and fixed and movable, screened to prevent overheating. Depending on their size, the window and shutter are opened in different ways. Wooden slats protrude externally in a variable manner depending on orientation of the sun path and shutters. When open, are always incorporated within their overhang so as not to alter the perception of the architectural composition and to be protected from the weather. The orientation and sizing of the new openings and the choice of light colors for the internal finishes guarantee, unlike the pre-intervention condition, good levels of quality as found by the analysis, daylight autonomy, the DA, and the UDI. And values are for the ground floor DA 56.9% and UDI 74.90%. For the first floor A from 14.76% to 61.32% and UDI from 74.10% to 85.70%. And for the second floor, DA 64.02% and UDI 70.10%. The first analysis of the project states are effective in achieving optimal output values as you can see in these figures. The use of biorepresent material of half-tone line applied to the opaque structure there is excellent inertial property with phase displacement value of about 24 hours. The improvement is mainly due to the reduction of thermal energy exchange by transmission and of the reduction of the dispersion of the perimeter wall and of the roof. There is also an 84% reduction in the demand for summer air conditioning with a useful energy factor for cooling the of 2.74 kWh on a meter square per annum. Following the comparison of the simulations, the life cycle assessment analysis was carried out in order to understand the nature of the ecological nature of the project intervention. Actually, one of the goals of the study is to highlight the environmental benefit of transforming the building compared to demolishing and rebuilding it. The environmental product declaration APDD of the materials is making the considering in particular, among other indicators, the primary energy input PAI and the global warming potential. The results show that the production phase of the intervention produces a total of primary energy input value of 1,082,188 megajoule, 52% from renewable energy sources, and by a negative global working potential value of minus 1172 kilogram carbon dioxide equivalent. This value represents an environmental gain derived above all from the use of building material of plant origin. Moreover, the use of existing load-bearing structure avoids the consumption of 252,089 megajoule of non-renewable primary energy that would otherwise have been required in the case of demolitionary construction or the construction of a new load-bearing structure similar of the previous one, while saving 41,058 kilogram carbon dioxide equivalent. Therefore, it's as of the methodology used and the usefulness of breaking up building and demolishing it and constructing one in its place have been proven. And it is that I can further and please try to contact me on my mail if you want to know more about it.
Thank you very much for your presentation, Federica. And we open a question time. So is there any questions from the audience, or online audience? Any questions? You can ask by Skype, for example. Okay, so there is no question, so let's go to the next presentation. The title is Power Quality Improvements in Grid Connected PV System Using Hybrid Technology. The authors are Prasad Kumar Vandali Malapa, Herminio Martinez García, Guillermo Velasco Quesada, from the Department of Electrical Engineering, Escola de Ingeniería de Barcelona, Technical University of Catalonia, in Spain. In this case, we also have a video presentation. I think I think the alpha is online, so maybe he want to.
Online maybe.
Are you there, Prasad? So do you prefer to present online or the video presentation?
Video presentation is okay. You listen the video presentation. If you have any doubts, I can clarify the doubts.
It's up to you.
Yeah, you can carry on the video presentation.
Okay.
If you have any doubts, I can clarify the doubts.
Okay, thank you. Let's go ahead. Presentation. Atlante con el 4G va a ir bien.
Good afternoon. I am Prasad Kumar. I am going to present my paper on different events in grid content photovoltaic system using and my co with the maximum 4-point tracking system. So maximum 4-point tracking system is nothing but everything. So one is related to the binary. So it has three parts: three classification, rule based, definition. Classification is nothing but inputs are changed to positive. Rule based is the relation input output, and this is converted into non-fuzzy values, and which is used to control the photovoltaic system. And the fuzzy controller produces the value of direct duty cycle that given to the maximum power point technique, and fuzzy control modifies the duty cycle value of a PWM over pulse width modulation technique to produce the upper switching circuit, that is switching pulses. And similarly, another optimization technique algorithm is called adaptive algorithm. This algorithm is used for the optimization and cuckoo bird have nest. It must take into another bird nest. So that other bird we call it as host bird, and cuckoo is travel randomly by using effect. So nest it will take into the nest. So algorithm will add will keep expression on the left side, and second will random exponential on the out of host bird. The word host bird can identify the egg grow away, it abandons the nest and build a new nest. So it is on the fitness value of the egg. Once the egg is placed in the nest, it will identify whether the host bird egg is quality fitness is better than this. Then the solution will be host egg will take as a host egg as a solution. Unless we replace the new solution, that is the host bird can build new nest, and we can check the best quality of the egg, and that is given to the object. This one we will compare with the best one, and we will given the solution as a best egg. So next, moving on to the block diagram. So this is our approach. Now it consists of photovoltaic system. Photovoltaic system is given to the DC to DC boost converter. So once the fuzzy logic controller is given the duty cycle to the maximum power point tracking system. The process pulses. That pulses give DC converter to boost up the DC, and multi-level inverter it converts DC to AC. So for the optimization using the adaptive focus controller, and they are given to grid. And similarly, you can see the simulation diagram, which has according to the block diagram, the photovoltaic boost converter and DC to AC converter, that is the multi-level inverter, and this is linear pattern navigation. It doesn't have any algorithm. So with algorithm we are merging hybrid algorithm. This is nothing but we are going to search algorithm and fuzzy logic control. So the proposed algorithm produce the determined data of the duty cycle. The data that this extra duty cycle will be utilized for the pulse width modulation to input pulse for the switch of the converter. This increase the phase or decrease the value would be to reduce the constant present in the system, and that also develop the process of maximum power point and reduce the total stress. So the individual processor and hybrid functionality. I said for two different multi-level inverters. One is 5-level multi-level inverter, other is 27 level. So we have tested different artificial network controller and this RBJ controller, and this is our hybrid ACS and FSC controller. So compared to all other existing both are the performance of the valid analysis. Some of the existing technology, the following results in table. Next, we have conclusion future work. Effect is with the adaptive system of the output of the control system, and both physiological controller and adaptive the proposal method offers compared to the conventional RBI strategy. In the future, in this future can extend modifying the topology of inverter, because the multi-level inverter also one of the main to get less pronounced distraction. So we can modify the inverter and we can use the recent lower conventional technology to enhance the work. Thank you, Abra. Thank you.
Thank you very much for your presentation, Mr. Malapa. Now it's time for questions from the audience online. Please, any question? So, no question. Thank you again, Mr. Malapa, for a nice presentation. We are sorry about the quality of the connection, but we are experiencing some problems.
Yeah, thank you very much. No problem. Thank you for your attention.
Okay, so we move to the next presentation, which is adaptive notch filter based WECS for balance mitigation by M. Abbas, M. Mokhtar, M. Aymaray, A. El Sattar, from the Department of Electrical Power and Machines, Faculty of Engineering, Ain Shams University, Cairo, Egypt. This presentation will be online by the authors. Please, any author is online?
Yes, I'm here.
Okay, please can you share your screen with your presentation?
Is it okay? Can you see the screen now?
No, still not yet.
Not yet. Yeah, is it available now?
No.
Can you see it now? No?
I think you're not activating your sharing screen button. There's nothing shared.
So, can we see the video?
Anyway, maybe we can move to another presentation. Perhaps.
Maybe, okay.
You're fine. Okay, Mrs. Abbas, we can move, if you don't mind, we can move to the next presentation. In the meantime, you can solve your problem of screen sharing.
Okay.
It's okay? It's okay for you?
It's okay. It's okay.
So we will move to the next presentation, 297, a brief introduction in the mitigation of conductor electromagnetic interference issues by Mr. M. Budlugan from the Department of Buildings Engineering at Technical University of Cluj-Napoca, Romania.
Okay, thank you, Mr. Chairman. I guess yes, I had the bad luck to be here and not being online.
I will share your screen. Please.
Yeah. Yeah. Right. Right.
The presentation is online.
I'm online. Mr. Chairman, the technicians?
Yeah.
I'm online.
For a moment, please. We will share the right one. This is your presentation.
Yeah, yeah. That's good. Oh,
This one is for you.
thank you. Thank you. Mr. Chairman. Ladies and gentlemen, for the audience.
Yeah, it's online.
Yeah, okay, I'm online. Yes, thank you very much. This is the presentation of my paper. You have seen the title.
Click wherever you want.
Yes, the contents, it's the introduction, and in the introductory section, I'll present some brief notions of electromagnetic compatibility. And in the second one, I present the equipments and techniques for measuring conductive interference. Yeah. Using this equipment and these techniques, I'll pass to the third section of my paper, experimental results, where you'll see a modality, the most frequent modality of mitigating conductive electromagnetic interference. And finally, some conclusions. So, in the introduction of the paper, as I said, I'll perform a brief presentation of EMC. Yeah? EMC being electromagnetic compatibility, which is the ability of equipment of a system to function satisfactorily in its electromagnetic environment, and on the other hand, not permitting that the interference affect its operation. Here, in this, sorry,
I will share the screen.
yeah. Okay, thank you. In this picture, as you can see, figure 1, yeah, there is a twist structure of EMC. You can see that EMC is divided in two big parts: electromagnetic interference and electromagnetic immunity. Yeah? Interference means that an equipment or a system could be disrupted in its function, in operation, by any electromagnetic perturbation. On the other side, immunity represents the possibility of the equipment to withstand of these perturbations. A lot of technical problems, yes? Okay. Both electromagnetic interference and electromagnetic immunity are divided in radiated and conductive. Yeah? Conductive emissions presumably are important in the frequency range from 100 kilohertz until 30 megahertz. Yeah? And beyond that limit, standardized limit, the radiated emissions are considered. It's normal that nothing magical happens at 30 megahertz, but the idea is that the cables and used for these frequencies tend to excite some resonance frequencies after third resonance frequencies after 30 megahertz. On the other side, radiated no problem, and immune and vaccinated. Okay, on the other side, radiations are not how to put it, in the low frequency domain, yes, until 30 megahertz, radiative perturbations are near field radiations, which are not propagating, which are reactive radiations, and the results are not really convincing. Yes. As you can see, for electromagnetic immunity, ESD, electromagnetic discharges, are also present here. So, we pass to the equipment for measuring techniques and equipment for measuring this conducted interference. Perhaps I should say that conducted interference means the interference which are propagating from their source by cables, by port cables or by signal cables, and they are not radiating in the air. As you can see in figure 2, these are the equipment that I used in the next section to measure conducted interference. There is a spectrum analyzer and line impedance stabilization network. This line stabilization network, as you can present, basically a low-pass filter, and it has two major objectives. First of all, it presents a constant impedance of 50 ohm, and on the other side, another goal of the line impedance stabilization network is to block conducted emissions, yes, so that we can measure only the emissions of our EUT equipment under test. Yeah. Okay, let's pass to the other slide. Thank you very much. But it's very important here in conductive interference, it's a dichotomy between the differential current and the common mode current. As you can see in figure 5, yes, I represented both the differential current and the common mode current. It can be seen that the different current enter to line L and exit to line N. Yeah. So as with the main current, yeah, the different in this case represent a perturbation. Has the same path as the normal current. On the other side, yeah, the common mode current operate differently. Yes, as you can see, the common mode current, common mode perturbations, electromagnetic perturbations, which are determining this common mode current, yeah, has the same direction for L and N, and he tend to close on the PE, on the protection electric port. As you can see, if there is no path for the common mode currents are closing through the parasitic capacities which close in the equipment between the main lines and the housing of the equipment. So here we have some loops. Yes, loop 1, which represents the differential current, and loop 2 and loop 3. Yes, you can see in the text on the left, yeah, which represents the common mode currents that are closing here in this equipment. It's important to say, that generally common mode currents are more aggressive. Common mode perturbations are more aggressive than the differential ones. Okay, and also I think that here something happened because of the laptop. No, it's no danger. It's okay. So as you can see in figure 6, yeah, the common mode currents also can deter and deter also deviations more important than the differential ones. As you can see in figure 6, yeah, the E net, the intensity or the strength of the electric field, it's much higher in the case of common mode perturbations than in the differential ones. Yes, you can see there that, how many minutes? 15. 15, okay. Sorry. Yeah. Okay, that the strength is more important in the case of common mode currents. Okay, let's go further. Yeah, here some experimental results. Yes, considering the electromagnetic emissions conducted through the power cord of an equipment. It is an induction motor, as you can see in the picture at the right. Let's go further. So the most important possibility, or the most important manner to mitigate or to even to cancel this electromagnetic conducted interference is using the EMI filters. Yes, you can see here in figure 8 the typical topology of mains filter. Yes, and the most important part of this filter is the common mode choke, the one with those inductance there, which are common mode coupled. Yes, and here you can see in figure 9 and figure 10 some simplified equivalent circuit for differential mode filter and common mode filter. That means that this type of filter, EMI filter, can mitigate both differential and common mode perturbations. Here I also presented, yes, detailed schematics of the EMI filters containing also the parasitic elements of slit when we think about their operation in the frequency range from 100 kilohertz to 30 megahertz. Yeah, each of these elements of circuit, resistance, inductance, capacitance, have also parasitic behavior. And in figure 12, you can see that considering these parasitic elements, which I called hidden schematics, obviously the schematics of the power EMI filter is a little bit more elaborated. Okay, let's go back. So here I presented the setup for those EMI filters. And here we have the attenuations introduced by two categories of filters. Why two categories of filters? Because I presented previously the topology of an EMI filter, but in our case, it wasn't enough only a single cell of filtering. And so we implemented and we designed and then we implemented cascaded EMI filtering, yes, which is composed of two filtering cells, and after that, the result of in the left you can see the two characteristics of the two filters, and in the right there is the final characteristics of the cascade. Let's do it. Yes, and after retrofitting this cascade, the results was presented in figure 19, where the limits are not exceeded. Yes. So it's very important to think matters in the frequency range. Lately, very important because due to power electronics and due to the electronic devices and to the digital devices are more frequent than earlier. Yeah. And therefore, retrofitting a TMI filter may be considered a very cheap and a very effective modality to mitigate the electromagnetic perturbation. Thank you for your attention.
Thank you very much, Mr. Portugal, for your presentation. So we open a question time. So any question from the audience, please? From the online audience?
I wasn't interesting.
Okay, 5 people, yeah. So we are a bit late on time, so thank you very much again for the presentation, and we move to the next one. Thank you very much.
Thank you.
So maybe we can recover the presentation from Mrs. Abbas. Are you ready, Mrs. Abbas?
Yes, I'm ready. I'm not sure that the problem is solved. I'm gonna try to share screen another time.
So please try to share your screen again. Maybe you need to exit and enter again the Skype application, or maybe I don't know if you are using the web version of the native application.
No, the application, not the web version. Okay, it's not seen right now, right? The screen hasn't appeared, right?
No, we don't have the screen. We can see it. We can't see the screen.
Okay, I'm going to exit and enter.
Okay, no problem. Para último que tenemos vídeo, Hugo.
Sí.
Vídeo.
El último que vamos a compártela. ¿Va a probar?
¿Quién me tiene el micro abierto? No todavía, ¿ya?
No, me he quitado la... ¿Compartido ya? Compartido el micrófono completo.
Okay, so we move to the final presentation, waiting for Mrs. Abbas. This is unfavorable reactive power in a rolling mill. The authors are Stanislav Novak and Stanislav Kochman from the Department of General Electrical Engineering at the Technical University of Ostrava, Czech Republic. sé qué se está escuchando.
Okay, I've entered again. I'm going to try the share screen. Okay.
Mrs. Abad, please wait for a moment. We are trying to present now the last video, and then will be your time.
Okay.
¿Por qué no se escucha nada? Es que hay como un micro abierto que yo creo que la entrada de audio la estoy usando por otro lado. Hay aquí un micro abierto y no sé qué.
The presented paper describes electric power consumption at a rolling mill. It was an opportunity to investigate the active and also reactive consumption at some points of the main supply system at a rolling mill. Since the last modernization, the whole rolling process is
Okay, let's start again from the beginning.
Dear ladies and gentlemen, first, I would like to thank the organizers for the opportunity to participate in this conference. Dear conference participants, the presented paper describes electric power consumption at a rolling mill. It was an opportunity to investigate the active and also reactive consumption at some points of the main supply system at a rolling mill. Since the last modernization, the whole rolling process is controlled by a large structured DCS. The process is, of course, monitored by operators who intervene only in the event of non-standard situations. Rolling is a metal forming process in which a metal stock is passed through many pairs of rolls to reduce its thickness and to make the profile of the rolled material uniform. A pair of rolls represents the main part of a rolling stand. Most of the rolling stands are driven by DC low-voltage motors. By the newly installed rolling stands, AC low-voltage motors are used. Mechanical power on the axis of individual motors is in the hundreds of kilowatts. The speeds of the individual motors are precisely and separately controlled for each motor. The motors are powered by DC converters or AC frequency converters. The whole factory is connected to the public grid at 110 kilovolts level. The power is transformed in the transformer T2 to the 22 kilovolts level. Two rolling mills are powered from this transformer. The investigated rolling mill is powered by the transformer TP2 connected to the secondary winding of the transformer T2 on the medium voltage level of 6 kilovolts. The following points were selected for the measurement of the consumptions. Point marked 1 at the main inlet of the rolling mill from the transformer TP2. Point marked 3 at the cable going to the substation R5. The access to this substation was not permitted. Point marked 4 level. Here, I would like to mention two in principle different units that perform almost the same function. They both serve to compensate the reactive consumption. The former unit, installed at the beginning of the rolling mill, is the synchronous condenser. Since the beginning of the operation of the rolling mill, its main function has been the compensation of the undesirable reactive consumption. This large electric machine has been running for decades and is still carefully maintained in reliable operation. As it turned out during the evaluation of the measured data, its compensation ability is not sufficiently used. The latter unit is the filter compensation unit based on the two sets of the serial resonant filters. The total capacitive consumption is about 6 megavolt amps reactive. This slide presents the time course of the total active consumption measured at point 1 during 4 rolling cycles. The time courses during the individual cycles are quite similar and correspond to the passage of the rolled material throughout the process. The active consumption P1 varies from 9 to 12.5 megawatts. This slide shows the time course at the same point at the main inlet. The time course of the total reactive consumption corresponds to the mechanical load of the rolling mill. From the time course, it is clear that the consumption is not controlled, although the presence of the synchronous condenser would at least allow rough control of the reactive consumption. This is the key finding that will be discussed in more detail at the end of the presentation. Here, you can see the time courses of the synchronous condenser active and reactive consumptions. The active consumption is almost 80 kilowatts. This consumption is irreversibly lost as useless heat. The slightly changing time course of capacitive reactive consumption of the synchronous condenser proves that the excitation current is not controlled. The active consumption on the inlet of the later installed substation R5 shows the direct dependence on the instantaneous mechanical load of the first 4 rolling stands at the start of the rolling process. At times when active consumption is at the level of 1 megawatt, these 4 rolling stands run idle. The filter compensation unit is a part of the substation R5. Its capacitive reactive consumption significantly exceeds the reactive consumption of here-powered drives. As a whole, the substation R5 is significantly overcompensated. The presented courses show that the control of reactive consumption is not given the necessary attention at the rolling mill. On the left, you can see the time course of the reactive consumption of the rolling mill again. The areas where the rolling mill is unnecessarily overcompensated are marked in red. On the right, I recall the uncontrolled time course of reactive consumption of the synchronous condenser. Certainly, There are possibilities for an improvement by changing the excitation of the synchronous condenser. Another option would be to turn off the synchronous condenser and thus achieve the annual saving of approximately 650 megawatt-hours. These options will be the subject of further detailed investigation. Thank you for your kind attention.
Thank you very much for your presentation. I think we have the authors online, so we open a question time for the audience. From the people here in the room. Okay, so we are a bit late, so we need to move to the last presentation. Mrs. Abbas, it's your time, please. Can you share your screen? Let's try.
I've shared my screen. It's available.
Okay, we can see your screen now.
Okay. Okay, start.
Okay, so please remove the okay, yes, we can see the presentation now. Please go ahead. Mrs. Abbas, please go ahead.
Continue. Is there a problem in the connection?
No, it's okay. You can start, please.
Okay. Okay, I'm going to present my my paper. That does not filter based wind energy conversion product. It's not as huge, considering COVID-19 and the lockdown measures in 2020, which led to reduction in the energy consumption and mainly energy produced from fossil fuels. Despite that, renewables, specifically solar photovoltaics and wind turbines installations, have continued growth. As shown in the figure, the growth rates for wind turbines and solar distribution of renewables, distributed energy resources, also known as decentralized energy resources.
Mrs. Abbas, I think we have lost the connection, or the connection is not good, because we are always seeing the first slide.
Renewables.
Mrs. Abbas, can you hear me? Something is wrong with the connection with Egypt, I think. Mrs. Abbas, can you hear me?
Okay. Yes, I can hear you.
I think the presentation is frozen, something like that.
Okay.
maybe some problems with your connection, internet connection.
Okay, can you hear me? Can you see the presentation?
We only see the first slide of your presentation. Okay, now we see another slide. I think the second one. So we miss you. What you were telling us. We were not seeing your slides, I think. So you can start over, please.
I'm going to yes. Okay.
Okay, thank you.
My paper, Adaptive Notch Filter-Based Wind Energy Conversion System for Unbalanced Mitigation. The world has witnessed a large growth in the renewable energy resources installation in the last years, despite the COVID-19 crisis and the lockdown measures, which led to a reduction in energy consumption, and especially energy produced from fossil fuels. Despite that, we can see that renewable energies, specifically solar photovoltaics and wind energy turbines, have the greatest growth rates in the last 3 years, as shown in the following figure. Distributed energy resources, which is also known as decentralized energy resources, have consequently increased following this huge expansion of renewables, since they depend mainly on renewable energy sources. So, these distributed energy resources are replacing the central power plants. These central power plants were traditionally used to provide ancillary services besides delivering electric power. So, the need for ancillary services has increased. Moreover, the presence of these renewable energies, due to their intermittency, so they need to be balanced, and the more need for ancillary services has become. Okay, and this sources. But now the only alternative for ancillary services, for providing ancillary services. Our proposed system is a wind energy conversion system connected to a tertiary winding transformer and applying some local loads. The first objective was to utilize a tertiary winding transformer instead of 2 transformers, one for connecting the wind energy conversion system to the low voltage load, and the other for stepping up the voltage to the medium voltage grid. Then, the power quality problems encountered by the auxiliary loads were mitigated, such as voltage regulation of the low voltage loads and unbalanced detection and compensation. Finally, our proposed system can contribute to the grid by providing ancillary services through active and reactive power control of the wind energy conversion system. Okay, the wind energy conversion system includes 2 main converters, the machine side converter and the grid side converter. The machine side converter is used for maximum power point tracking of the wind turbine. It is used and load balancing. For the grid side, for the DC link voltage regulation and the load voltage regulation, since where 2 PI controllers are used to control the direct axis current signal, current reference, and the quadrature axis current reference signal. Then these 2 signals are then transformed to the ABC reference frame to get the switching pulses for the converter for the grid side converter. The reactive power supplied from the wind energy system is limited to a maximum of 15% of the active power to avoid any overloading of the converter. To detect the unbalance or to extract the positive and negative sequence current components, an adaptive notch filter algorithm was proposed. This adaptive notch filter algorithm works on 3 loops. The first loop is used for frequency estimation with a sinusoidal signal. Then the second loop is used for line extraction of the fundamental current component and its 90 degrees phase shift signal. This fundamental component, along with the negative, with the 90 degrees shifted signal, are directly used to get the positive and negative sequence through symmetrical components matrix, linear symmetrical components matrix. Other traditional methods used previously in positive and negative sequence extractions were the synchronous reference frame based algorithm and the fast Fourier transform. In the synchronous reference frame algorithm used before, the load currents are transformed to the DQ reference frame in synchronously rotating frame, and then a second order notch filter is used to notch the negative sequence component, thus leaving the whole signal except the negative sequence component. These currents are then transformed to the ABC reference frame using the transformation angle from the phased log loop circuit, then are subtracted from the original load currents to get the negative sequence components current signal. Also, the FFT, or the fast Fourier transform based algorithm, is used to estimate the positive and negative sequence and implemented to compare these three methods for detection of the unbalanced component. Of the proposed system was done using PSCAD EMTDC program, and different case studies were conducted. First, to ensure that the machine side converter is pursuing the amount of the wind turbine, different wind speeds were introduced. And as can be seen, the rotational speed of the wind turbine keeps changing as the wind speed changes to track the maximum point on the power curve of each speed. For easier analysis, to check the voltage regulation loop and the unbalanced mitigation loops, we've only set the wind speed to change from 5 meters per second to 13.5 meters per second at 6 seconds simulation time. So as seen here, as the wind speed changes from 5 to 13.5 meters per second, the rotational speed of the wind turbine, it changes so as to track the maximum power. Meanwhile, the voltage of the DC link is kept constant, and this is done by changing the reference signal of the direct axis current controller. Then the power of the wind turbine delivered by the wind turbine and the power delivered to the grid are shown here. At the beginning, the wind turbine output power is below the requirements of the load. So the grid contributes with the wind turbine to supply the load. After the wind speed has increased to 13.5 meters per second, the wind turbine supplies both the load and the grid. At 13 seconds, the load was increased to test the voltage regulation loop. So as can be seen here, as the load increased, the quadrature axis current component increased to keep the voltage of the load constant. And then after at 16 seconds, the load is decreased again. So when the load decreased, the quadrature axis component current has decreased to keep the voltage constant. As can be seen here, the voltage of the load is kept constant at 0.38 kilovolt. At after any disturbance, it's always kept constant. Hence, the voltage is regulated for the low voltage load. For an unbalance of 46% was introduced at the second 8 of the simulation time, and can be seen here, the three previously mentioned methods, FFT, synchronous reference frames, and adaptive notch filters, were compared. So as can be seen here, the adaptive notch filter exhibited the best performance, the most accurate, and the fastest conversions to the negative sequence component, same as the positive sequence. The load unbalance compensation control loop was enabled at the 10th second. So as be seen here, the grid currents were unbalanced, but after compensation of the negative sequence, it's now balanced. Meanwhile, the load is still unbalanced. So also another case of unbalance mitigation, the imbalance was decreased to 30%. And as seen here, the three methods tracked the change in the negative sequence component, and also the adaptive notch filter was the fastest method to determine the negative sequence and the positive sequence components. For the load compensation, for the unbalanced compensation loop, it was disabled at 17 seconds. So before it, the grid currents were balanced, and then it became unbalanced again. Okay, the load currents are always unbalanced. So we've presented here a distributed energy resource wind energy conversion system with some added control actions to perform some ancillary. The voltage of the local loads is kept regulated at different loading conditions, and also the imbalance mitigation was achieved under different unbalance cases. Three methods for unbalance detection were compared, where the fastest and most accurate method was the adaptive notch filter. Thank you for.
So thank you very much, Mrs. Abbas. Question time. Any questions from the audience? Is there any question? So we are almost out of time. I'd like to thank you again for your patience, Mrs. Abbas. We have some problem, but we could solve it. So thank you for all the authors, and with this presentation, I close this oral session. So thank you very much, everybody. And now we close the session. Thank you.